Greetings. Today I want to solve a problem on combustion. The difference that a combustion problem makes with other thermodynamic problems is that in different thermodynamic problems, up until now, we had one or two incoming streams and one or many outgoing streams. And the point was that whatever that entered the control volume also exited the control volume, and it was the same. In our previous chapters, we learned that if we have a mixture of gases entering the control volume and a mixture leaving, still all would be the same. So perhaps some sort of composition would change. I mean, the combination, it was in the previous chapter where we had air and water vapor entering the control volume. Sometimes there was some water which vaporized, and also the molar ratio of the composition changed, but still it remained water and air. Water and air entered, water and air left the control valve. And in this chapter for combustion, we have a different problem in that when fuel enters, say some sort of fuel enters, and air enters, which basically means oxidizer. So it is O2, which usually has 3.76 N2 with it, and that is the ratio between oxygen and nitrogen in the air. Now, whatever lives is totally different. It is CO2 plus H2O and N2. In a perfect combustion, in an ideal combustion, all fuel, which is some sort of hydrocarbon fuel, which is, say, it is CXHY, okay, uh, the ideal combustion assumes that all carbon finds oxygen, all hydrogen finds oxygen, and so we have CO2, H2O, and N2 doesn't enter the combustion and just comes in and leaves. Of course, in the real combustion, not all carbon finds two oxygens, so there might be CO, and also there might be some oxygen which haven't found carbons, and therefore there will be some oxygen, and also nitrogen could enter the uh, combustion and produce NO or NO2 or NOx as it is called, which are all pollutants. So what we do now for the time being is just assume that there is perfect combustion. In the present problem, we will solve the combustion of ethylene. And with combustion of ethylene, we assume 20% extra air. So it is more likely that all carbon would find oxygens for it, and there would be some extra oxygen leaving the combustion chamber. So our fuel is C2H4, C2H4, plus our oxidizer is air, which is O2, plus 3.76 N2. And first we do ideal combustion and see how many moles of O2 we need. And then what we do is to uh, make it 20% more. So if we do the combustion equation, then we would have CO2 on the right hand plus H2O, H2O, and plus N2. Now, how do we balance the equation? There are two carbons, and therefore there would be two CO2. There are four hydrogens, and there would be therefore two H2O, and there are four oxygens here, two oxygens here, therefore uh, we have six oxygens, and therefore if we put a 3 here, we would have six oxygens here, which is enough oxidizers for both CO2 and H2O. And finally, we just have to multiply 3 by 3.76 and calculate whatever N2 that enters this combustion. So it would be 11.28. Now, the problem tells us that there is 20% excess air. So what we do is to write it down as C2H4 plus 3.6, which is 20 point excess air or 120% theoretical air, as it's usually called, times O2 plus 3.76 N2, and that produces 2 CO2 plus 2 H2O. Now there is some oxygen that couldn't find any carbons because there's extra air, so there would be plus 0.602. That's the zero point 0.6 oxygen that we added here, plus 13.536 and 2, and that's our combustion equation. So now we know whatever that enters our control volume, whatever that leaves our control volume, and the problem that we want to solve is to see how to calculate the enthalpy and the entropy of whatever that enters our control volume and whatever that leaves our control volume on the same basis. It's important to note that we should have the same basis for both enthalpy and entropy, and we have to assume our enthalpy of formation just to account for the fact that C and H should leave its bound. The bound between C and H will be broken, and new bound between C and O and H and O would form. So we have to write our equations in a way that accounts for such breakage and such joining in order to be able to calculate our enthalpies and entropies. Now, the question we want to answer is that how to calculate the enthalpy of reactants. Now, reactants are fuel and air. So, the enthalpy of reactants, which is fuel, oxygen, nitrogen, is composed of two parts. So we need sigma NiHi, and that is the enthalpy of reactants is the total of its moles plus its enthalpies. Each we have to repeat it for our CuH4, O2, and N2. We know the number of moles, but what do we do with the enthalpies? The enthalpy Hi is composed of two parts. First, the enthalpy of formation, which is written in this way and is given in tables different books, and that is the enthalpy of the bond. This is how much energy is used to join C2 and H4 or to break them. That is part of the energy that they have. We didn't use this energy up until now since there was no breakage in the chemical composition of different substances that we had. If H2O entered our control volume, H2O also left our control volume. But now, since there is a breakage in the bond between C and H different, the bond between different atoms, therefore, what we need to do is to account for the energy required to break that bond, and that is described as enthalpy of formation. So it is H standard F plus, of course, it is the sensible enthalpy, and that's exactly what we used to calculate before. But we have to take into account one point. The point is that what's the basis for calculating enthalpy? And the point for this one is that we're free to choose a basis for enthalpy in the first law of thermodynamics before. Today we're not. It's not the same thing because the enthalpy of formation is given at 298 degrees, 298 Kelvin in different books. And also, there would be a different enthalpy involved if, say, the enthalpy of oxygen is selected from 0 Kelvin or 298 Kelvin, and this difference would be different from what there would for N2 and what there would be for CO2. I mean, the difference between the enthalpy of CO2 from 0 to 298 would be different to that difference for N2. So we have to have the same basis for all of them, and that basis is selected to be 298 Kelvin, 25 degrees C. So what we need to do is to um, present our enthalpies on the basis of 298. That's the standard that is set and used in different books, and therefore we also follow it. We use still for different items, O2, N2, CO2, H2O, we use the same tables as before, but we have to use them twice. Once we have to use them for the temperature that the reactants or the products are, and also, again, for the enthalpies of the reactants for the products at 298, and therefore deduct them, and then that would be the way it is presented. Now, so we do this for both reactants and also for products. So what we need to account for is HF, H at 298, and H. The point with this term is that often we assume that reactants are at 298. So this term would basically be zero for each of these three. That's the simplification, but it doesn't have to be always like that. There are tables which give us different values of C2H4 as a perfect gas at different temperatures, or give it CP at different temperatures, and we calculate H for C2H4 and other constituents at different temperatures. So it is possible to do it, but for the time being, we just assume that all reactants are at 298. So this term would be zero for each of these three. But for the products, no, that's not the case, and you have to calculate both the enthalpies for them at 298 and also read it for tables, enthalpies at the temperature of the products, and deduct them to find all enthalpies of these products at the temperature of the product. Now, as before, it's a good job to have a table which gives us different reactants and different products, and also the properties that we need to calculate for each of them. Just this row coincides with the with whatever I have written here. I mean, all the different elements are represented here, and their number of kilomoles for each of them is just produced here. It's just the same as what we had in our um, equation, and therefore we have it all. Now, you see, usually for the time being, for this problem, we assume that fuel enters differently at uh, 1 atmosphere and 298, and air enters in a different channel at 1 atmosphere. So these are two different. So as for fuel, N equals 1, and Yi would also be 1, as you see, but O2 and N2 enter together, and therefore their molar fraction would be 0.21, which coincides with the same ratio. I mean, these two are added together, and each number of moles is divided by the sum, and so this one would be 0.21, and this one would be 0.79. We do the same practice for the products. As for products, they are all together. Their total pressure is 1, and therefore their molar fraction for each of them would be 0.11, 0.11, 0.03, and 0.75. These are the molar fractions for the products. Now, the other thing we need to do is to go and read enthalpy of formation for all the elements that we have in our equation. This is just what we need to read from the table, and if we do that, what we get is that enthalpy of formation is 52,280 for C2H4. It would be 0 for O2 and N2, and also for CO2 and H2O, we have different values from the table, and O2 and N2 would again be 0. As for sensible enthalpy, we could read it also from the table, and if we do that, the enthalpy of our fuel is given as 0, since the base point for the fuel for presenting it is 0. For O2 and N2, these are the values that we read and we produce it in the table. Of course, the point is that they enter at this at 298, and this is also the enthalpies at 298. So the H minus H at 298 would be 0 for all three of them because they enter at 298. Nevertheless, at 2250, the enthalpies of the products would be different. We would also read all of these values, enthalpies at 2250, as we assume we start with the value that the products are at 2250 Kelvin. Let's have a small think. Why did I assume the product temperature to be 2250? Where did the value come from? And now I explain it for you. And I shall continue with the rest of this combustion problem in the next video. Cheers.